Okay, well, we have today Professor Neskash.
Good morning.
Professor of Technical University, Leibniz, Czech Republic. It is indeed a pleasure to have Professor Neskash with us, and we have an opportunity to get his wisdom, what he has put in last 35 years
Yes.
of his work, and what he is going to cover in this particular course. He is going to talk about his this new ideas, new concept, logics to come out a particular aspect of this particular subject, that is your theory of textile structure. And in this particular course that he will cover a good number of lectures, where that he is going to talk about helical model, his equidistant migration model, compression model, and at the same time that he is going to talk about the theories what we have studied in the literature, like one-week theory, Taylor or Hall models, and there that with his own idea that he has tried to drive his own equations and try to work out what are these assumptions have not been considered earlier. He has taken care of all these issues, so that these equations now, or this information what we are going, so we can say this is updated in today's context. And another aspect that which can be noticed from his lecture, whatever modeling that he is doing, that he experimentally that he tries to prove this concept, so that the logical concept which he has taken into consideration in his lecture can be experimentally seen. With this, now I will request Professor Neskash to start his lecture.
Thank you for your nice introduction.
Thank you.
I want to say you hi everybody. Well, let's come to our first theme. Let's come to the theme compression of fibers assemblies. The compression is a very important process in textile technology. We compress fibrous material, for example, by creation of non-woven textiles. We compress the fleece by bonding process. We compress fibers inside the yarn, therefore we twist, and so on and so on. So that the compression is very interesting and very important process. We can be sure only about the one only in one moment. It is that this compression regulations don't follow known Hooke's law, so the linearity between the force and deformation effect. It was a lot of people earlier which studied this problem. The knownest name is C.M. Van Wyck, and about the Van Wyck theory I won't speak in this first lecture. Then I will mention also our own alternative by some generalization of this theory, but it will be in the second lecture. Van Wyck was some scientific person. It is, when I say Van Wyck, it is like Van Gogh or Van Dyck, some Holland Dutch painter, but he wasn't from Holland. He wasn't painter. He was a scientist in South Africa, and he studied the compression of fibrous material to the bales. It was interesting to know how is the relation between the pressure and the volume of bale. Theory of Van Wyck started with some assumptions, as each theory. He assumed that the fibers are straight, acylindrical, having diameter d. I have constant length L and are random oriented. What is it, the fiber contact you see on the scheme in our slide? It is this one, the contact of two fibers. One contact represents two contact points. When you give some small drop of red color between these two fibers, then you will have 2 points, two contact points. One contact is 2 contact points. Fibers in the structure have a random distribution of their orientation. How to characterize this fiber orientation? It is necessary to characterize through some unitary vector, such vector like a vector I on our scheme. Of course, fiber, let's imagine that this is fiber. Fiber is not arrow. Fiber have not the character of arrow, so that this direction and this direction are for fiber only one direction, isn't it? Therefore, we use some convention that we will use the half sphere for vectors, which will characterize our orientation of our fiber portion or fiber segment. It exists couple of two angles, an angle theta to x3 axis and angle phi to xy axis, which characterize direction of unitary vector and so direction of our fiber or fiber portion. Angle theta is going from 0 to pi by 2 because we use only half of our possible sphere, and phi is from 0 to pi. Because no write too long form, we will use symbol omega as a domain of fiber directions. It means that the omega is theta from 0 to pi by 2 and phi from 0 to 2 pi. Because the orientation of fibers is random, we need to work with some joint probability density function of couple of quantities, couple of angles, theta phi. This PDF is called as W. So that evidently integral over all directions from such joint probability density function is equal 1. For spatial fiber location, we need to know two informations. Let's imagine that this is some fiber portion. We need to know fiber direction, maybe it is here. Okay, but the fiber segment can be here, or here, or here, or here. All these fiber segments have same directions, so that it is not enough. We need also fixed one point of this fiber, for example, at the end point. When I say the end point is here, then and the direction is early given direction, then it determines together one original fiber segment. Each theory of compression needs to solve two problems. The first is to solve contacts, fiber to fiber contacts, and the second is to solve the mechanical rules which are valid. The first part must be also about the fiber contacts. 1 week have based on my meaning, very genial very genial idea. He said, we know from geometry the situation which is, for example, in our first picture, the penetration of couple of objects, maybe two cylinders, because our idealized fiber now, it is some cylindrical object. In geometry, it's possible to penetrate cylinders. You know it from the descriptive geometry and similar courses. And one week is meaning that if two abstract cylinders mutually penetrate, then the couple of real fibers, it is not possible to penetrate, they are from material, they are from matter, from mass, then the couple of fibers will be in contact. So, on the place of this geometrical position, he said, in reality, the final position is this here. So, he transformed the first question about the contact to the other question about the penetration of two cylinders, geometrical cylinders, which represents geometrically our fibers. I said we speak about the random-oriented fibers. So, how is the probability that two fibers will have mutual contact? The idea is given in this picture. Let's imagine two fibers, fiber number 1 and fiber number 2. Fiber number 1 is in our scheme this fiber, idealized, straight, cylindrical, as we said in first sentences of this lecture. Yes, this is fiber number 1. Let's imagine that we know direction of this fiber, vector I1, as well as the position in the space. So this fiber is fixed in space. Let's imagine that we know also the direction of fiber number 2. We know direction, but we don't know the position of the fiber in our space. Such fiber having the direction y2, unitary vector y2, can be here, can be here, can be also here. I speak about a fiber. In this moment, I mentioned the theoretical cylinder where the penetration is possible. So, in this case, and a lot of other cases, such fiber number 2 will not penetrate fiber number 1. Nevertheless, in this position, fiber number 2 will penetrate the fiber number 1. It based on the position of endpoint X on the fiber 2. It's evident, at first intuitively, then, if this endpoint X is lying inside of this oblique prism, then the fiber 2 will penetrate through fiber 1, where no will not penetrate. How to construct such oblique prism? It's relatively easy. We know the axis of the fiber 1 because fiber 1 is fixed in the space. We can each fibers have the same length L. So from the point which is point P, from the point P we construct straight line length L in the direction of fiber 2. We obtain the line PQ, isn't it? Similarly, from the point S, we create a similar straight line, and so we obtain SR. And for points S, R, Q, P, define some plane. Perpendicular to this plane, we construct some line, and on the distance D, we have the point A, so PA is length equal D. And similarly, from the other side, PE is also distance length D. The same we make from point Q, from point R, and from point S. And so we obtain such oblique prism. You can a little think that when this point X is lying inside of this oblique prism, then the contact, so the penetration, exists. If no, then this couple of fibers have not some contact. How is the probability that fiber 2, which is randomly is in a random position in our space, that the fiber number 2 will penetrate fiber number 1? It is the probability that the point X is lying inside of this oblique prism, and this probability must be given by the ratio of two volumes. Volume of our oblique prism V12 by total volume of whole fibrous assembly Vc. A volume of this oblique prism is given as 2 times d times L squared times S sinus psi, where psi is the angle which is between given by the direction of both fibers. It's evident from elemental geometry. Nevertheless, let's remember that the angle psi, which is here, must be the function of these two directions. It means first direction, it is couple of informations, theta 1, phi 1. Second direction, it is theta 2, phi 2. So four quantities define our angle psi. Theta 1, phi 1, theta 2, phi 2. Yo? It is not unknown equation. It is not unknown relation. It is very known from basic laws which are valid in geometry. For example, we obtain cosinus psi as a result of so-called scalar product of this couple of unitary vectors, and scalar product is something very known. So it is a very known function which gives psi as a function of four quantities, theta 1, phi 1, theta 2, phi 2. Yeah? Well, Vc is total volume, and the probability is V12 by Vc, evidently. So that the probability is given using this expression by such equation. Well, it's geometrical definition of probability, of course. We know the probability that fiber number 2 will be in contact with fiber number 1. Now let's study number of contact places on our fiber 1 from all fibers. Fiber number 1 have angle theta 1, phi 1. Fiber number 2 have direction given by couple theta 2, phi 2. One fiber we select as a fiber number 1 from all. Each other fiber can play the role as fiber number 2. So that number of fibers which can play such a role, possible fibers number 2, a number of such fibers is N2, capital N2, which is total number N minus 1, because one fiber we select as a fiber number 1. Probability density function of fibers number 2 is which of? And PDF, probability density function of all fibers direction, is the W function of general theta phi. Let's imagine fishes in all oceans in the world. The lenses of these fishes have some probability density function. It is characterized by some probability density function. Let's imagine that you fish one mackerel and you give the fish out from ocean. How you change the probability density function of lenses of fishes in whole oceans? Theoretically you changed, but this change will be so small that we can say we don't change this probability density function, isn't it? Similar it is here. When we think about the fiber assembly from very high volume of fibers, which usually is so, then we can say when we take one fiber, we select one fiber to the position as a fiber number 1, the probability density function is not changed. Therefore, although the fibers possible as a fiber number 2 have the same function W, and this probability density function I will call as a VW theta, W theta theta to phi 2. Now let's imagine some elemental class interval. You know from laboratory what is it class interval, you use it by evaluation of your experimental works, experimental research from laboratory and so on. Let's imagine the idea that we have infinitely small class interval. Let's imagine that it is so small class that the angle is going from some value theta to some value theta plus d theta. D theta is differential quantity which is higher than, which you can imagine as something which is higher than 0 but smaller than each real number. Differential quantity is infinitely small. So let's imagine that the interval is from theta 2 to theta 2 plus d theta 2, elemental short interval. And similarly, phi is going from phi 2 to phi 2 plus d phi 2. Such class I call as a elemental class. And from theory of probability, it's known that probability density function times these two differential quantities have some logical sense. It represents logically something. It is relative frequency in our elemental class. Relative frequency and or probability, because relative frequency and probability are two very similar terms. When we obtain such value after our experimental experiences, we prefer the term relative frequency. When with the same quantity we use as a how to characterize possible future, then we speak about the probability. Well, so that the relative frequency of fibers, I will for short say fibers having direction theta to phi 2, but more precisely lying in elemental class from theta 2 to theta 2 plus d theta 2, from phi 2 to phi 2 plus d phi 2. Yeah? In short, I will say fibers having direction theta 2 phi 2. Number of fibers in this elemental class is which of? Total number of fibers number 2 and minus 1 times relative frequency w theta 2 phi 2 d theta 2 d phi 2. Well, for following derivation, let's assume that such configuration which is here, we will not, about such configuration we will not think. It means if two fibers are in contact and third fiber would like be also in third orange fiber want also to be with contact with fiber number 1. This situation we will not think, so that we can write how is the, if this assumption is valid, then we can say how many contact places on the fiber number 1 is from the group of fibers having direction theta 2 phi 2. All fibers, number of all fibers was dn2. But not all fibers are in contact with our fiber number 1. Only some of them. It's based on the probability. Evidently, the probability, the number of contact places is probability times total number. Isn't it? Yeah. So, using our equation for probability and our equation for number of fibers having direction theta 2 phi 2 in our elemental class, we obtain this expression after small rearranging this expression. But it is not too important for us. We want to know how is the total number of contact places on our fiber number 1. What we need to do? We need to sum these contact places over all fibers number 2, all other fibers, because to obtain total number of contact places of fiber number 1. What is it to sum it over all directions? Wilhelm Leibniz, this special sum called by the alphabet S. But because it was a little mixed with another alphabets, they used more and more longer alphabet S, and today we call this very long and slim alphabet S under the term integral. Therefore, we use symbol of integral. Yes, we must integrate it, so that the number of fiber contacts on the fiber number 1 is integral from this expression, this here, over all directions. After rearranging, we obtain M1 in this equation, like this equation. Okay, we solved the question how many contact places are on our fiber number 1. But we need to know how many contact places is lying on all fibers in our fiber assembly. How to do it? We will use very similar way, logical way. Number of all fibers is n. PDF, probability density function, is w theta 1 phi 1, because each fiber can be, we can choose each fiber as a fiber number 1. So it is w theta 1 phi 1. Elemental class interval of fibers number 1 is given by these two intervals, and probability density function is w, so that the relative frequency is v function W theta 1 phi 1 times d theta 1 times d phi 1. Well, number of fibers in such class is dn1, total number of all fibers times relative frequency. Sure? Sure. And the number of contact places on the fibers with direction theta 1 phi 1. How is number of contact places on the subgroup of fibers, but only these fibers which have the direction theta 1 phi 1. This direction, no other. How it is? It is number of contact places per one fiber times number of fibers having this direction dn1. It is dm. So that dm using expressions derived earlier is this here or this here. Yes. And finally, how is the number of contact places in the whole fibrous assembly? Now we must sum contact places over all fibers so that it is integral over all fibers which can play the role as our fiber number 1. So over omega 1. We obtain this and then this horrible, very terrible expression. Nevertheless, don't be worried, it is not too difficult. This is formula for number of contact places in all fibers in our fiber assembly. What seems so horrible? It is this integral. But what is in? And xi, it is a known function of theta 1 phi 1 theta 2 phi 2. We mentioned it earlier. Then we have here only one function W. In the first position, the variables are theta 1 phi 1. In the second, in the same function, only the name of variables are added, theta 2 and phi 2. When somebody of you give me the analytical formula for function W, I can, to solve this integral and in the result say you, how is this value? This is a value, this is definite integral. Resulting is value, some real value, something between 0 and 1 it is. So this value, this integral, which we, by the way, we call this integral I, is the function of a fiber orientation only. It's enough to know probability, joint probability density function of couple theta phi, the function W, no more. We need not more. Well, we can say that the I, the value I, is some characteristic of fiber orientation in our fibrous assembly. It is some orientation characteristic. You know other statistical characteristic like mean value, standard deviation, I don't know what, coefficient of variation. And this is a little atypical, but also some statistic characteristic of distribution given by this joint probability density function W. Well, therefore, this equation we can write symbolically in this easier shape, where I is some characteristic of suitable characteristic of fiber distribution of fiber directions of fiber orientation. It is number of contact places in whole fibrous assembly. Number of contacts, because every time two contact places create one contact, is 1/2 of this. So number of contacts n is given by such expression. Now let's solve the density of contacts. Density of contacts, it's fiber volume we obtain using this way. Fiber volume is which of pi d squared by 4 fiber cross section times L volume per one fiber times number of fibers. It is fiber volume. Vc is a total volume, and you know from first lesson that it is fiber volume by packing density, fiber packing density. So that total volume using on the place of V this equation is this or this. Density of contacts, it is we mean as a number of contacts per volume unit of fiber assembly, N by Vc. Using such equations derived, we obtain after rearranging this here or this here. It's only easy rearranging. And what is this? This is independent to packing density, this quantity. So this is some parameter related to fiber orientation as well as fiber diameter. So some material characteristic which we call K nu, and we can say that the density of contacts, number of contacts per volume unit, is proportional to square root of packing density. In mean distance between adjacent contact places, how it is with mean distance of contact places? It's easy. Let's imagine the red fiber which is in contact with black fibers here. This length, these portions from contact to contact, we call as a delta. So mean value of delta is which of? When you imaginary bonded together all fibers, let's imagine that I give to each contact some drop of red color, and then I take each fiber and bond it one fiber beside the other, so I obtain from my fiber assembly very long fiber. Length of such fiber is n times L, n fibers times length of per one fiber, and on this very long fiber will be number of all contact places, m. So that distance between adjacent contact places, delta bar, is nL by m. M is 2 times n. Using our equations after rearranging, small rearranging, we obtain delta bar is this here. This is parameter independent to packing density, so we can call it as the K delta, and we can say that the mean distance between adjacent contact places in inverse proportional to packing density. Well, we solved the first part of our problem. We solved the questions about the contacts. Why? Because by pressure, the force which we, or the pressure which we use is going to other fibers, or the forces are coming to the other fibers through contact places between fibers, not through air. Air is not hard. Well, so contacts we know. Now we will start with compression. We will solve the easiest case, so one-dimensional deformation. One-dimensional deformation is shown schematically here. Let's imagine some starting situation of our fibrous material in some non-deformable box. Packing density mu0. Now, using the pressure P, our material is pressed, and then the final situation is shown here. The fibrous material have smaller height, now C0 than C, and the packing density is increased from mu0 to mu. based on the influence of pressure P. So packing density beginning is mu0, finally is mu, pressure is P, and the deformation is from C0 to C. 1 week means that the dominant deformation of the fibers by pressure is a bending deformation. Of course, generally all imaginable forms of deformation can be, but maybe it's well that the dominant character of deformation is a bending deformation of fibers. 1 week also thought that we can, roughly of course, as an assumption for simplification, we can use the knowledge which know our colleagues from mechanical engineering. In a mechanical engineering is solved some beam, some infinity long beam, which is shown here, where the forces is lying in the middle of this fixed point here. This is the traditional problem from our colleague from mechanical engineering. They solved it using such Clapeyron theorem or three-moment theorem. We will not to repeat this. Only we will write now the result from our colleague from mechanical engineering. The solving of such deformed beam give following couple of equations. The acting force F is proportional to the ratio Y. The ratio Y is shown here. It's a deflection of this beam by this distance h power 2, 3. Yeah? So, this is the first result of our colleagues, and the second is that the length of beam, this length is h times some function, some increasing function, monotone increasing function f of ratio y by h. Of course, when you will read some teaching book for students of mechanical engineering, on the place kf you will have some more structural quantity, some ratio in which is shape of cross section of beam and Hooke's law and so this E, this Young modulus and so on and so on. But altogether we can this function call only f and this parameter call as a kf. These two equations we will use also, but we must accept that these equations was derived for very small deformations and using Hooke's law. So it's for us only a rough result. But because in the moment we have not something better, it must be enough good for us. Yeah? Well, the real structure of fiber assembly is random and it's very, very complicated. We must make our picture of this structure a little more easy and regular and also random. So that let's imagine our structure. Let's imagine our structure as a more regular. Let's imagine that our fiber have some shape like some beam, and around there are another fibers here. So this is similar than this picture. And around our fiber exists some area dimension x0, y0, z0 in starting position, where is some air, so that the packing density of this unit, the structural unit, is mu 0. After compression, let's imagine that from such structural bricks, a whole structure is created. You can repeat these bricks, left hand side, right hand side, before, behind of this, yeah? And so from these bricks to construct whole fiber structure, idealized because regular, no, only random. After pressure on this yellow area, using the pressure P here, the brick is deformed. Because we solved the one-dimensional deformation, we imagine that our box is non-deformable box from some steel. Then we obtain from this position a new final position of our structural unit, of our brick, and also number of contacts, because higher packing density will be higher. Well, how we will solve this question we will explain in our second lecture. So I thank you for your attention. Be happy.